Welcome back to the channel, everybody. And today we'll be discussing a bit further into the YDSE experiment in the wave optics, and then after that we'll be starting with the diffraction. So let us begin. The first thing that we need to understand is the change of slit width that occurs in the YDSE. So the important thing that you need to understand is I'll draw the YDSE experiment first once again. Let this be small d, and now let this be the width, this be capital D, and from here we are shining in light. So I'll just make some waves. Yes, these are the light waves, not rays. Just for representation I have shown them as a straight line. So the thing to understand is the intensity on the screen. This is our screen. So the intensity of light produced on the screen, if each slit is producing an intensity I naught, slit is producing an intensity I naught, then this intensity is directly proportional to the width of the slits on the double slit plane. This means this plane, we are talking about this plane. So yes, this is something that we need to know, as we all know. Yes. So this was the first thing. Now the second thing is the power of a particular slit is given as I naught, that is I naught L and W. We know that W is the slit width, and what is L? Then L is this. This is the sorry, actually width of the slit. I should write this as L and this as W. So L is the length of the slit and W is width of the slit, and I naught is the constant. And now from here we can, at a distance from a slit, if we are asked at a distance from a slit, this is important because till now we were taking everything from the central bright, this point C, but now we are taking it from a particular slit. So this is something quite interesting to remember. So intensity of a particular point x can be given as I of slit is equals to P of slit upon pi xl, and then we can expand P of slit from this above formula, which is very important, as I naught L W upon pi Lx. This LL gets cancelled, so it is I naught W upon pi x equal to I of slit. So this is a particular thing once again to remember. And now let us get to understand another thing, that is interference in thin films. Just a minute. So the light is getting reflected Let me draw a particularly thin film for our understanding purpose. I'm drawing it large. This is our thickness T, and there is this light which now I'll be drawing by green color that arrives at this point. Let me use this too. Yes. That arrives at this point. That yes, and two things would happen. One, the light would get partially reflected over there, and the other thing would happen is that the light would get refracted inside, and there would be a bending. Yes, so this is our incident ray, this is our reflected, and this is our refracted. So the reflected ray theta over here, theta incident, this would be theta refracted, theta r means refracted. Yes, so now the only thing to start on from is, so I should label these points as P, Q, R, and then yes, one more thing to note that you might have totally forget is this light would go over here and some of it would again get reflected. So it would go out like this and then again get refract and go out again. So I'll draw this and I'll draw this, and now I shall label these points as, let me label those in other color so as for your quick understanding. So this is P, Q, let this be S, let this be P, Q, R, S, T, U. Yes, that's it. So now the instant thing that should come to your mind is that these two lines must be, okay, I'll use another color now. Something that should come to your mind is that this two must be the same, and now if I draw a perpendicular onto this line and this line too, then this also is same. As this angle both are same, so this both must be same as due to similar triangle concept. So now let us write the path difference between the rays P, Q, R and the ray P, S, U. I am writing this like this. So PQR, let we put a perpendicular over here as we did in YDSE, and this length is the extra length that the PQR ray traveled. So it is RQ. So I'll write it as Q. Oh no. Let this be an point M. QM. So let this be QM of the ray PQR, and as you can see from the diagram itself that PSU has travelled much more distance, and for the path difference we need to subtract these both the distances. So I am going to add a subtraction as for avoiding the negative. There is a mod outside after all because it's a distance. And now let us understand the extra path travelled by PSU. So till PQ, both the rays PQR and PQU, PQR and PQSU, They both were traveling till PQ the same distance. After that, all the changes happened. So the ray PQSU has traveled QSU extra, while on the other hand, the PQR ray has traveled QR extra. If you put a perpendicular and understand it. So QST is the extra part that both the ray PQSU has traveled. So we know that while traveling from a slab, the path difference is mu minus 1 times t, as discussed in the previous lectures. So we'll use that over here. I'll make the circle in another pen. Use that over here. And then we write mu times no. While traveling inside, the wave would have a change that is due to the optical part and the delta, and henceforth it would take more time. So we write mu into t minus 1. T minus 1. Sorry. Extremely sorry for this. So yes, I would like to correct myself that when a particular wave travels inside another medium, so as derived in the optical part derivation, we write mu t minus t. This is the t that it has that the wave has traveled this much distance in a particular time. So we write mu minus 1 times t. This is the formula, and to derive this formula, this is the path that has been traveled by the ray. So we have to write this, and hence we write a mu outside, and now the t, that is the path traveled. Over there it was the thickness, and now here we have to write QST. As we know, QS is, I'll write it QST, and now we just have to put in our values. Okay, let us assume this theta r. Yes, we have, and we know that QS equal to ST. Just now we proved it. QS equal to ST, and now we have to write QST. So it would be, I'll write it over here as QS equals to ST equals to mu into 2 times QS minus QM. So now what is QS? This is our R, that is our theta R refracted angle, and this is our QS. So if this is QR, then this must be theta R. So in triangle QSN, if we see this length, we know the T, so we know this T. So in order to involve the T as well as the QS, so we can use over here the triangle QS. Okay, just a minute. This is the T and this is QS. In the triangle QSN, if we see itself that this is T, I'll draw the triangle QSN over here because it's a very hodgepodge diagram. So this is our T and this is our theta R. So in order to find QS, we assume it as X, and adjacent side upon opposite side is sine of, sorry, adjacent side is the cos. I'm extremely sorry for making so many mistakes today. Is equals to t by x. So x equals to t upon cos theta r. Now we substitute this x over here, and now we get mu into 2 times mu as the 2 comes out, and then t upon cos of theta r minus of qm. So now what is qm over here in the diagram? It is the extra part traveled by the ray PQR, that is the reflected ray. So in order to know the reflected ray QM, we have put the theta there, and let's use the triangle property once again. This is our theta I, we know it. So this is our theta I, this, so this would be 90, this angle would be 90 minus theta I, and as the other angle is 90, this angle would be theta I. So let us draw our triangle of there. This is theta I, this is QM. The diagram is not accurate, but still for understanding we can use it. This is T. Okay, and we can write QT. Let us first get QM in terms. So for QM we will need, this is a 90 degree over there. Actually the diagram is not up to scale. Let me resketch the diagram. So for QM we need opposite side, and for that we use sine of IC. I'll write here in triangle QMT, sine IC equals to the opposite side, that is QM upon QT. So now the task is to find QT. So QM equals to QT into sine IC. Now let's see in the triangle where QT is. So QT is the angle which comes in the theta r, or else we can write QT also in terms. So QT equals, QT is, it is the hypotenuse, actually this is the hypotenuse. So so let us see in the triangle QSN what the QN stands in. So it gives us in this triangle, it gives the tan, that is if we use tan, sorry for the cos, tan of theta r is equal to the opposite side, that is Q1 upon the adjacent side, that is ns, that is equal to t. Ns is equals to Q1 upon t. So we write Qn equals to t tan theta r, but as it as we know, qt equals to twice of qn, so is equals to 2t tan qr. I'll write here in triangle qsn. So I'm substituting 2t sine theta r upon cos theta r into sine of IC equals to qm. And now I'm applying the simple Snell's law, assuming the outer as this is air and this as a refractive index of mu. So by Snell's law, we say that sine of sine I theta I equals to mu times sine of theta r. So now substituting this over here, we get 2t sine theta r upon cos theta r into mu times sine theta r equals to qm. And now 2 mu t outside, it's sine square theta r upon cos theta r equals to qm. Now substituting this in 1, I'll name this equation 1 as it's very confusing. Yes. So it is 2 mu t upon cos r equals to 2 mu t upon cos theta r minus 2 mu t sine square theta r upon cos theta r. So now we can take 2 mu t upon cos r theta r as common, 2 mu t upon cos theta r 1 as common, and we get 1 minus sine square theta is equals to the part difference, 2 mu t upon cos theta r into cos square theta r. So 1 cos theta gets cut, so delta x equals to 2 mu t cos theta r. But this is not the end of it. As we have learned in the waves, that if a wave goes from the medium of rarer density to denser density, then there's a shift in the wave. It is the ray is reflected, then the ray is transformed by, it is rotated by 180 degree, that is by pi, and this is the ray. So it gets reflected and it gets, like, you can say, rotated too by pi by 2. So now we know the phase difference between them is then plus some delta x dash of reflected. I'll write it as rotated. So we know that delta x equals to lamb upon 2 pi into phi. So lamb upon 2 pi into the phase difference there becomes pi, that is 180 degree. So the part difference over here becomes lamb by 2. So we add this lamb by 2 in this equation, and then we get finally the path difference, that is 2 mu t cos theta r plus lamb by 2. This is easy, not so hard to derive, just a bit of complications here and there, else everything is sorted. Yes, so let me put it in red. And now we can plug this delta x for conditions for bright spot. And if you see then the results are exactly opposite of what we expect. So for minima we write 2 mu t cos theta r plus lam by 2 equals to, this is the path difference, is equals to, for bright spot it is n lambda, and upon solving we get 2 mu t cos theta r equals to 2n minus 1 lam by 2. This is a very interesting result, as it is exactly opposite of what we have seen in the YDSE experiment. And if we go further and we derive the condition for dark spots, then we get 2 mu t cos of theta r plus lam by 2 equals to the path difference, which should be equals to 2n minus 1 lam by 2, and over here upon solving we get 2 mu t cos of theta r equals to n lambda. This is again exactly opposite of what we expected in YDSE. So there should be no confusion. Hence, I have remembered this part difference very clearly instead of those conditions. And as I have mentioned earlier, we just have to focus on deriving the path differences in these questions. Only then the questions would be framed, would be solved. So let's go further and understand one of the last things, that is wedge shaped film. So a wedge shaped film is something like this. You must have seen a wedge in our kinematics, and so if a ray falls on it like this at an angle, pardon me, like this at an angle, then let us assume it goes along the normal, that is like this. So it goes inside, there is this surface, and this ray it would hit. Some of it would even get reflected along the same path, because we are assuming 90-degree with the normal, and then some might also. But for a generalized case, I am writing the formula for path difference. We will not waste time in deriving it because it is just simple. 2 mu t cos theta r, that's it. This is the formula. There is no lam by 2, and the reason for it being that there is no phase change. There is no inversion in the ray. Hence there is no change, and from here on you can derive everything. And another thing, which is the fringe width beta, which can be written as 2 upon mu tan two mu tan theta. So now no, I'll change the angle because theta I've already used everywhere. So let this be alpha. So these are some of the things that you may need in the questions that you might solve. So with that, we complete most of the part of the YDSE. We'll meet in the next episode in order to study the diffraction. Yes, thank you. Meet you soon.